Here we go. All right. So I have two vectors, A and B. If I added them, as we just did, so if I did A plus B, then I would draw a vector that should be the same length and direction as that, and then B so that would be A plus B, the stuff we just did. A minus B is, I draw my A again. We'll pretend that's the same length as that. And then B, we're adding in a vector going in the opposite direction to that. That's negative B. So my resultant is this. So multiplying, recognize vectors, if we break it up, have two parts. Well, we just did it. When we went from polar form to rectangular form, we had a horizontal part and a vertical part. Now, there's nothing special about horizontal and vertical other than just the way we have been trained in math. I can also break A up into perpendicular components so that one of them is along the direction of B and one of them is perpendicular to D. So let's draw that over here. Again, I'm going to assume that's the same length as that, like A. And I'm going to exaggerate a little bit. Yeah, I'm going to make B longer just because. So if I break A up into perpendicular components, I have some angle, theta, of course, which is the angle between the two vectors. And so I have the perpendicular components here. This I'm going to write as A parallel and A perpendicular. So there's part parallel to B and part perpendicular to B. One of the big differences between dot products and cross products is which one we multiply by. So if I do A dot B, and I'm hoping you can guess that this is why it's called a dot product, I multiply parallel. So it's the magnitude of the parallel part of A times the magnitude of B. The absolute value symbols here represent magnitude. So the magnitude of A, we have a couple ways of writing that, of course. The magnitude of A can be written as just A without the vector symbol. There are times when this can be very misleading, so even though I will do it, there are some times that I will not do it just because of confusion. Or I can write it as the absolute value of A. Well, this component down here, this part that is parallel to B, I got a right triangle. We've done this several times today. This is just going to be A times the cosine of theta, the hypotenuse, times the cosine of the angle to get me this adjacent side. This over here is going to have a magnitude of A sine of theta. So my dot product will yield the magnitude of A times the cosine of theta times the magnitude of B, or just A, B cosine theta. Another important difference between a dot product and a cross product is a dot product gives you a scalar answer. This is a scalar. There's no direction in the final answer. So this is sometimes called a scalar product. And I will flip back and forth between which term I use. Cross products multiply times the other one. So A cross B, I'll tell you the magnitude of it. It does produce a vector, but writing out the vector piece of it gets complicated at this point. So A cross B, the magnitude of A cross B is going to be A times B times the sine of theta, because you're multiplying times the perpendicular piece. But cross products does produce a vector. So this is called a vector product. For the purists in the group, it actually produces an axial vector or pseudo vector, but axial vectors and pseudo vectors look, smell, and taste exactly like vectors for this course. The difference shows up when you start getting into the higher levels of physics. All right, so dot product cares about the parallel, cross product cares about perpendicular. And a memory trick there is that if you think about a cross, that's perpendicular to each other. And so we will deal with this in chapter, let's see, 4, 6, I think chapter 7. And this is chapter 9. That's when we get into that in more detail. I do touch on dot products briefly in chapter 2, but we don't do much with it at that point other than justify a derivation. All right, questions to hear, because we're about to actually officially call chapter 1 done. All right, because chapter 1 is officially done, the quiz. If you've gone onto Blackboard under coursework, clicked on chapter 1, you'll notice that there's videos, yeah, but there should be, if you go down, a place that says textbook homework problems, I think something like that. And if you click on that, bring up the PDF, you will see a slew of problems. Now, with solutions. The quiz is, I'm going to take 2 of those problems, I'm going to change the numbers, that's going to be the quiz. If you like surprises, you never have to open the document. It is not necessarily a good tactic to take, but some students have opted for that. And I'm pretty much sure that there's been only one student who has successfully pulled that stunt off. But it was also the second time he took that course. So, again, not my recommendation. So the question is when? I'll look over there because that's where I used to write that stuff down. So today is, with all that stuff in the wrong place. All right. I think for the chapter 1 stuff, I think a week from today. Quiz on chapter 1, the homework, what I generally call the homework quiz. A week from today. So next Thursday, I will start out with, are there any questions on chapter 1? And when that is exhausted, or I feel like we need to do the quiz, we will stop it and do the quiz, and then we'll do a class. Now, there are other chapters. Chapter 1 does not have it. Other chapters will have something called a master set. So when chapter 2, we're officially done with chapter 2, we will assign when the homework quiz is and when the master set is due. Master set is something that is handed in. The textbook problems are not handed in because I gave you the solutions. So I pretty much feel how that would be graded. But master sets would be additional assignment. They are former test problems. Probably should go through and update them at some point, but not this semester. So the master sets would be an additional quiz grade. Any questions right now?
You said that starts after chapter 2?
No, first master set is for chapter 2.
Is for chapter 2. All right.
So as we go through chapter 2, even though we're not officially done, you should be able to look at the master set and be able to do some of it. All right. Chapter 2, motion. Officially, it's one-dimensional motion. I've already talked about some of the vocab that we had there, so let's bring them up again. So we got these vector quantities here. Let's see if we can go something darker. Position. The symbol for position. I tend to use X a whole lot. Some textbooks really shy away from that. They stick with X only for horizontal motion and Y for vertical motion. You know, X is whatever direction I say it is. So, but X, S is often used, R is often used, and then sometimes Y, Z. Those are the typical letters that are used to represent position. And position is where an object is with respect to the origin. I'm going to put 0 in parentheses there. If it's a number line, yes, a number line has a 0 on it. We typically not call the origin, but in reality it's the origin if you have only one dimension. So if I say that I hat is in that way, assuming Amy was right with her earlier statement, then the position of the door, if I am the origin, the position of the door is 15 steps I hat. That's the position of the door. If the door is the origin, then its position is 0. And my position would be, well, if I hat's in that direction, my position would be, if the door is the origin, negative 15 steps I hat. The nice thing is that for most problems, you get to decide where the origin is. However, there will be a test, at least one test problem, where I tell you where it is. Don't worry, we will do practice problems, and I will say, hey, you'll have a problem very similar to this on the test. Displacement. The symbol for displacement is basically a delta, capital delta, in front of whatever letter you're using for position. So it's delta X, delta S, and so on. It's just the capital delta, which means change. So we can define displacement as the change in position, or where an object is with respect to the starting point. Those problems start somewhere, and then you go to the positive or negative side. there are really two types of displacement. There's instantaneous and average. Instantaneous and total. If I just say displacement, I mean total. So I'm going to write down instantaneous. And total. And this is the default. So I have an object moving around and I ask what's the default, or sorry, what's the displacement? I'm asking from the very beginning of the problem. If I want the instantaneous displacement, in other words, where is it relative to where it just was? Then I would say instantaneous displacement. So I've got a coordinate system right here. I got a point right here. We're going to call this my initial position. So we're going to call this x sub I hat. X of I, not I hat, x of I. I for initial. My initial position right there is a vector going from, there we go. That's my initial position. I then move around and I end up over here. This is my final position. My displacement, implied total, is the difference between those two. It's where am I relative to where I started. That in blue right there is my displacement. From a math point of view, change is always final minus initial, always. There are not a lot of always in physics, and this is one of them. So that would be the final position minus the initial position. All right, so let's go through a little exercise right here. I'm going to be moving back and forth in front of the board. I'm going to make this my origin. That's 0 right there. I'm going to make to the right positive. Positive I hat if you want, but if it's only a one-dimensional problem, I can get away with just a positive sign. So right now, my position, positive, negative, or 0?
Positive.
Yeah, I'm on the positive side of 0, because again, where am I with respect to the origin? I'm on the positive side, so my position's positive. I'm going to make this my starting point right here. Actually, considering the way the camera's working right now, I'm going to make this my starting point right here. So, my position now.
Negative.
My displacement.
0, 0.
Yeah, because I'm at the starting point. All right, so now, my position.
Negative.
My displacement.
Negative.
Everyone can play. My position now. My displacement? Yep. Position now? Displacement? Okay. Velocity. We have two ways of doing that one. It is the change in position over the change in time. Sometimes written as the rate at which position changes. Or how fast and in what direction. So velocity, the plus minus 0 or positive negative 0 for velocity doesn't really care where I am, it just cares about where I'm going. So let's explore the math just a little bit here. So technically, my average velocity would be displacement over time. Anyone here had Calc 1 or in Calc 1? 1, 2, all right. Instantaneous velocity is the calc bit, is the first derivative of position with respect to time. So if you haven't gotten to, if you're in Calc 1 now and haven't gotten to derivatives, at some point you're gonna see that and go, oh, yeah, I know that. All right. If it's total displacement, you're finding the average here. If you'd find the instantaneous velocity if you're looking at the instantaneous displacement. As implied right there, there's two types of velocity. There's instantaneous and average. If I ask what is the velocity, the default is instantaneous. If I want you to tell me what the average velocity is, then I will explicitly say average velocity. All right, so the same starting point and origin. So questions to here before we do the plus minus 0. All right, my position. There we go, that's what we're doing. My displacement. My velocity. All right. Get the running start here. My position. Displacement. Velocity. Velocity cares about which way I'm going. I'm going in the negative direction. My velocity now. And now? My velocity? Oh, it started too late there. All right, try that again. My velocity? Displacement? There we go. Position? Yeah, that was a positive, negative, negative for those who missed it. The symbol for velocity, as mentioned earlier, is a V with a vector symbol over it. All right, so I'm racing Usain Bolt. Racing around a track. We start off at the same time. He goes around the track, and in 30 seconds. I go around the track in 200 seconds. Let's take a look at the velocities. My average, what is, and we'll just make it 400 meters all the way around. Let's talk about speed. Actually, before I do that one, there's one other bit of vocab we need to do. Yeah, I'm gonna come back to it. Sorry. I typically do this in a slightly different order, and that's what's throwing me off here. All right. Ignore my race against Usain Bolt. I was about to show you how I'm as fast as he is, but we'll get to that in a moment. And you too can be as fast. Actually, hell, I'm actually faster than he is. And you too can be faster than he is. Acceleration is the next one in line. That's A with a vector symbol, since we're doing vectors here. There's indeed average and instantaneous, just like we did before. And instantaneous is the default. However, for a lot of what we do, the instantaneous and average will be the same thing. It's going to be a constant acceleration. Not for everything, but if in doubt, it's instantaneous. The average acceleration is equal to the change in velocity over the change in time. And instantaneous acceleration would be, in essence, change change in velocity over change in time, where delta t is infinitesimally small. The limit as delta t goes to 0. And it's basically the rate of change of velocity. Now, acceleration is a little bit trickier than the others. I think most people get an idea of, yeah, I'm going this way, and so my velocity is negative. I'm going this way, my velocity is positive. I'm not moving, my velocity is 0. Acceleration being positive, negative, or 0 is a lot harder for a lot of students to grasp. Acceleration deals with the change in velocity. Vector acceleration, change in velocity, not change in speed. I could be speeding up and my acceleration be negative. I could be slowing down and my acceleration could be positive, or negative, or we'll show an example of how that can happen. Time in seconds and my velocity in meters per second. Assume a one-dimensional problem. The reason why I say a one-dimensional problem, because in one dimension, my unit vector would be the same for everything. And everything would be I hat or J hat or whatever letter I happen to pick with a hat over it. And since everything has the same unit vector, I can just get away with not writing the unit vector and just do plus or minus. So let's say time is equal to 0. My velocity is 15 meters per second. At 1 second, it's now 10 meters per second. At 2 seconds, it's 5 meters per second. At 3 seconds, stop. 4 seconds, it's negative 5 meters per second. Oops, don't want to rewrite that. At 5 seconds, it's negative 10. At 6 seconds, it is negative 15. For the first 3 seconds, am I speeding up or slowing down?
Slowing down.
Yeah, I'm going from 15 meters per second down to 0. So I'm slowing down. What about from 3 seconds to 6 seconds?
Still slowing down, right?
If my velocity is 0, I'm not moving.
All right.
How can I slow down from that? Therefore, I'm speeding up. Yeah, so I'm speeding up here. The negative sign is just a directional thing. My acceleration is the change in velocity or the change in time. So if I look at from here to here, what is my change in velocity? Thank you. Yes. Change in velocity over the change in time is, it's always final minus initial. This is 10 minus 15 divided by 1 minus 0, or negative 5 meters per second squared. I get meters per second squared because the change in velocity is meters per second. My time is seconds, and so it's basically meters per second divided by seconds, which is meters per second times 1 over seconds, which is a meter per second squared. In the next second, what is my change in velocity? And it takes place over 1 second, so my acceleration here is negative 5 meters per second squared. What about the next second? The next second. See it? Negative 5, because my finals, so here the math is negative 5 minus 0 over 4 minus 3. So negative 5 over 1. What about the next one? My acceleration is constant the entire time. It's negative 5. But in this region, my negative acceleration meant I was slowing down. In this region, my negative acceleration meant I was speeding up. So a rule is, don't use that marker, if velocity and acceleration have the same sign, you're speeding up. Opposite signs, slowing down. So up here, my velocity was positive, but my acceleration was negative. They're fighting against each other, slowing down. Here, they're helping each other, speeding up. All right, plus minus 0 again. You need to respond quickly because I have limited space here. I'll start out slowly. My velocity, my acceleration. Why is my acceleration positive? I was speeding up right here. My acceleration was negative. Let's go back to this. I'm speeding up if they're the same sign. So my velocity, my acceleration, yes, they're the same sign because I was speeding up. It might not have looked like it, but I was supposed to be speeding up. I run like a middle-aged guy out of shape. Give me a break. My velocity, my acceleration, yep. Not everyone takes a fancy to that way of looking at it, so a different way of looking at it. We have not talked about forces, but I think most people have some inherent concept about forcing. They think of it as just a push or a pull. Acceleration, same sign as the total force. So if I'm walking in the negative direction, my velocity is negative. What if somebody pushes me from behind? Am I going to speed up or slow down?